All right, welcome, ladies and gentlemen, to the last section of our chapter 7. This is 7.5, obviously, if you're looking at that page there. This is the last of our identities. There are quite a few of them, so we need to get through all of them. All right, so let's go ahead and take a look at what this is going to look like today. These multiple angles and product to sum formulas, there's a couple of different ways that these are going to look. So the first way is having the sign of a multiple of an angle. And this would be something along the lines of like sine of 2x or sine of 3x or 4x or 5x, that sort of idea. So k is just any number. We're also going to be dealing with an identity that deals with sine squared or cosine. By the way, this works for sine, cosine, and tangent. We've got different identities for all of them. So we have one that deals with squares or a power reducing identity. We have ones that deal with half angles, though. So the sine of x over 2 or the cosine of x over 2 or the tangent of x over 2. If you have your green paper in front of you, you should be seeing some of these as we go through them. And the product of two functions. We have this type of identity as well. So we can take the product of two functions and rewrite them in different ways, just depending on what you have and what you've been given. All right, so let's go ahead and take a look at the first one, which is our double angle formula. So if you have your green paper in front of you, you'll see the double angle formulas for sine, cosine, and tangent. You'll notice that the sine of 2x is equal to 2 sine of x times the cosine of x. That's a pretty cool identity to have. And we could actually prove this identity using our sum identity from 7.4, saying that this is the sine of x plus x. And our identity says that means it's the sine of x times the cosine of x plus the sine of x times the cosine of x. Notice that the angles are the same. And if we add those two things together, we get twice of them. All right, so the sine of 2x works this way. The cosine of 2x has a slightly different variation where there's 3 different versions. And that's all of because the sine squared can change into cosine squared, and the cosine squared can change to sine squared using Pythagorean identities. I'll show you one of those here. So you'll notice that if I was to give you the cosine of 2x, I could say that is the cosine squared x minus sine squared x, and we can just create the other ones. Cosine squared is the same thing as 1 minus sine squared x. And I get, okay, the parentheses don't actually matter. I get 1 minus 2 sine squared x. All right, and the same fashion goes for the other version for cosine. All right, so let's see what we can do with these identities. So what I want to do is I want to solve this equation. And the only way I can solve this equation is if I can factor because of that plus sign. And right now I have cosine and I have sine, so I can't factor just yet. But if I was to know that sine of 2x has a different name, we can actually call this, we'll keep cosine x plus sine of 2x is 2 sine x cosine x. And now we can do some factoring. Both of these terms have a cosine. Actually, they both have a 2 cosine x. I factor that out, I get a 1 plus sine x. And this now goes exactly like we've been working on before. 2 times the cosine of x is equal to 0, which means the cosine of x is equal to 0. And here the sine of x is equal to negative 1. And the only times that this occur are when, for the first one, when cosine of x, x has to be pi halves and 3 pi halves. And the sine of x is negative 1 at 3 pi halves as well, and so therefore we only get these two answers. So notice we used that double angle identity right there. Another thing we can use with this double angle identity is rewrite this equation. One reason we would do this is if we were to graph this equation. This equation is not very fun to graph. However, its alternate is actually pretty easy. And what I'm going to do, since we're dealing with a double angle, I'm going to look for a double angle that kind of looks like this. But I don't really have one that looks like this. I have one that says 2 cosine squared x minus 1. And I can kind of do that here. I can factor out a 2. And I get 2 cosine squared x minus 1 by factoring out. And 2 cosine squared minus 1 is actually cosine of 2x. And this equation actually is very easy to graph. The amplitude is 2, and the period would end up being pi, so we would shrink it in half. And that's it. That's all we wanted to do in this particular equation. We wanted to rewrite using our double angle identity. All right, here's something a little bit different. If I've been given that cosine of x is 5 over 13, one thing we can do is, like we did in the last section, we can think about a right triangle where this angle is x, cosine is adjacent over hypotenuse. And if you've been paying attention to some patterns here, this is a Pythagorean triple of 5, 12, and 13. If you did Pythagorean theorem, you would get the opposite side of being 12. So if I wanted to find the sine of 2x, I can't just double this angle and double some sides randomly. That's not how math works. We would use this double angle formula or identity and say sine of 2x is actually 2 times the sine of x times the cosine of x. And sine x is going to be 12 over 13. And cosine of x is going to be 5 over 13 because we already knew that. So I get 5 times 12 is 60, times 2 is 120, over 13 squared, which is 169. And we just go along the same fashion in finding cosine of 2x. Cosine of 2x is just going to be whichever version you want to do. It doesn't really matter. Cosine squared minus sine squared. And since cosine is 5 over 13, I have to square that to get 25 over 169 minus sine, which is 12 over 13, so it's 144 over 169. And we get negative, what is that? 118 over 169, because I already have common denominators. And then if I wanted to do tangent of 2x, you can actually, it's not really cheating, just using a different identity. Tangent of 2x is just going to be the sine of 2x over the cosine of 2x. And that's going to be 120 over 169 divided by 118 over 169, which gets to be 120 over negative 118. And that's actually it. That's all you need to do for that problem. And of course I did my math wrong, not paying attention to myself. That's not 118, that's 119. Knew something didn't sound right in my head. Which makes this a 119 down here. Sorry about that. I'm sure you'll all forgive me. All right. Let me erase my writing here. Here's one here that's going to use a little bit of 7.4 and 7.5. So what we want to do is we want to get rid of that 3. Now, what we need to do is we need to think about this as a sum of two angles. And what we're going to do is we're going to say it's the sine of 2x plus x. And you're going to have to follow along here, obviously. If we get sine of 2x plus x, we can use our sum identity, saying it's sine of 2x times the cosine of x plus the sine of x times the cosine of 2x. And we need to go all the way down to sine. So this is kind of just a practice on using your identities carefully. Now, sine of 2x right here is not done yet, so I need to keep that as 2 times the sine of x times the cosine of x. That's just sine 2x. Then I have this extra cosine of x. And what I also want to do is I want to get rid of this cosine of 2x. And cosine of 2x, if I want to change everything to sine, I'm going to use my identity that says this is 1 minus 2 sine squared of x. And we're getting a little bit closer. Again, remember, this is one of those practice skills here. Using all of our identities, together. Now, what you'll notice right here is cosine squared x. Well, cosine squared x is actually 1 minus sine squared x. And what I can do over here is I can distribute my sine into both of these, and I get a sine x minus 2 sine cubed x. I'm going to do that down here as well. I'm going to distribute right here. And if I distribute right there, I get 2 times the sine of x minus 2 times the sine cubed of x plus sine x minus another 2 sine cubed of x. And now I can combine like terms. You notice that we have no more cosines left and a lot of like terms. So I get 2 sines and another sine makes a 3 sine x minus 2 and 2 makes 4 sine cubed of x. And there's our answer. We don't have any more cosines left. And we're down straight to sines. Okay, I'm going to just recap there. Notice that we took 3x and we split it into 2x and x. That's going to be a handy skill to do because we have a sum identity and we have a double angle identity that we can use along the way. Last little note here for double angle formula is the fact that it works for 2x, 4x, 6x, 8x, anything like that in this fashion. If I was to have the sine of 4x, the sine of 4x is just going to double up. So instead of having, so you know that sine of 2x is sine of x cosine of x. Well, sine of 4x is just going to be 2 sines of 2x and cosine of 2x. Where the sine of 16x is going to be 2 times the sine of 8x times the cosine of 8x. Again, another handy little identity to use, even though it's not on our paper. And it works for cosine and tangent as well. Okay, moving forward to our power reducing formula. Should have your power reducing formula there. And what that basically does is it's a way to get rid of our powers. our exponents, like that 4 right there. Oops. So what I want to do is I want to look at the sine of what we have. So, okay, so we have the sine to the 4th of x. And that's actually equal to the sine squared. And the reason I say this is because we have a power reducing for sine squared. And what we get is we get 1 minus cosine 2x all over 2. And that's sine squared. That's another way of saying sine squared. And then we're going to square that. And when we square this, the numerator we're going to have to FOIL. So if you need that written out somewhere, it's 1 minus cosine 2x times 1 minus cosine 2x. And 1 times 1 is 1. I get a minus cosine 2x. I get a minus cosine 2x. And here's where you need to be careful. Cosine 2x times cosine 2x is cosine squared of 2x. All over 4. All right, so let's see what we have here. Let's simplify that numerator. I get a 1 minus 2 cosine 2x plus cosine squared 2x. And what I want to do is I kind of want to get rid of this 1/4. So I'm going to factor out that 1/4 right out here, just for the time being. Now, technically, we're not done because the question asks you to write it into the first powers of cosine. And right now we have a second power. So we're going to have to use another power reducing identity, but this time for cosine. So cosine squared is going to be 1 plus cosine, and here's where things get a little bit interesting. The identity says cosine of 2x, but you have to understand that it's the double of whatever you started with. We started with a 2x, so my double is going to be 4x. And then what we can do is we can kind of distribute that 1/4 back in there. So I get 1/4 minus 1/2 cosine of 2x plus, now you got to remember that this was 1 over 2, so it's 1/2 times 1/4 is 1/8. And the same thing goes for the next one. It's 1/8 cosine of 4x. And I would be very happy if you guys got it this far. Obviously, you can simplify this a little bit farther. 1/4 plus 1/8 is actually 3/8. Oops, I don't know where that parentheses came from in my head. We get 3 over 8 minus 1 over 2 cosine 2x plus 1 over 8 cosine 4x. All right, so there you go. That is the power reducing formula. It's one of the big things that you're going to be doing in using that power reducing formula is doing this type of problem. All right, next. Like I told you, there's a lot of identities today. Today is the big one. All right, so half angle identity. And these ones look kind of ugly, but they shouldn't be hard to use. So what we're going to do is we're going to find the exact value of the sine of 105. And what we're going to do is we're going to use the half angle identity, not a sum identity, because yeah, we can do it 60 plus 45. But what I want to show is the half angle. So what I need to do is I need to first say that this is the sine of something over 2. And all you need to do is multiply this number by 2, and you get 210. And if you look at your identity, you have a u over 2. So this is going to equal the big square root of 1 minus the cosine of u. In this case, u is 210, not the 105. All over 2. All right, so then we just need to do the simplification. So we get the square root of 1 minus, all right, cosine of 210. Let's see, that is a negative root 3 over 2, I believe. Right, so that's a negative root 3 over 2, so this becomes a plus. All right, so now the fun thing of just coming into simplifying this radical, really. I kind of get the square root of 1/2 plus square root of 3 over 4 if you split this 2 to there and 2 to the other one. And I need to combine my fractions. So this is actually 2 over 4 plus root 3 over 4. So I get 2 plus radical 3 all over 4. Remember, that's under the radical. And last but not least, we need to square root that bottom piece. That square root becomes a 2 underneath the square root of 2 plus radical 3. And the only thing you have to pay attention to is that 105 is in quadrant 2, and sine is positive in quadrant 2, and therefore this is our answer. And what's interesting is you'll get an answer that looks a little bit different when you use the sum identity compared to this. All right, let's go forward to another problem here. Do the same exact thing, only with cosine. So we're going to say this is the cosine of 30 over 2. So 30 is now my u. And the cosine of u over 2 is going to be plus or minus, again, the square root of, in this case, it's 1 plus cosine of u, so cosine of 30, all over 2. And we're going to do the same thing as before. So we get the 1 plus square root 3 over 2, all over 2. And you notice this actually ends up being the same answer. So this could become 2 over 2. We get the square root of 2 plus radical 3. Using the same process as before, we get this. 15 is in quadrant 1. Cosine in quadrant 1 is positive, and therefore we keep this as a positive value. All right. Oops, too far. What we want to do is we want to solve this equation. And we are going to solve this equation using a couple different identities here. So we're going to leave 2 minus sine squared x alone for a moment. We're going to take care of this this x over 2. So we get 2 times cosine of x over 2. So we got to think about this as the cosine of x over 2, all of that squared. So we get the square root of cosine of x over 2, just like we figured out a minute ago, was 1 plus cosine of x all over 2. But we are going to square it so the thing does not look as ugly as it did before, because that square comes along. And we get 2 times 1 plus cosine x all over 2. The 2's actually cancel, and you're left with a 1 plus cosine x. Now, because this is cosine here, I actually need to change this sine squared into cosine so I can actually solve. So I get 2 minus 1 minus cosine squared x distribute that minus, I get minus 1 and a plus cosine squared x. So this becomes 1 plus cosine squared x. And lo and behold, this question actually becomes, oops, I don't know where that square came from. This actually becomes a pretty simple question. Subtract the 1s from both sides, subtract the cosines, we get the cosine squared x minus the cosine of x is equal to 0, which now all we have to do is factor cosine x times the cosine of x minus 1, which means the cosine of x is equal to 0, and the cosine of x is equal to 1. And 0 happens at pi halves, 3 pi halves, and cosine of x equals to 1 at 0, and 2 pi, but we don't need the 2 pi. All right, so that's our half-angle formulas, how we're going to be using them. We can use them to solve, we can use them to find exact values, and we can use them to verify if necessary. All right, another one, product to sum. So what we want to do is we want to be able to rewrite a product as a sum or difference. So the cosine of 5x times the sine of 4x. If you look down there, you actually have an identity at the fourth one, I think, where it is the cosine of u times the cosine of u times the sine of v. So the cosine times the sine of two different angles. And this is going to be 1/2 times, if you just follow your identity here, the sine of the sum of the two angles. So our two angles are 5x and 4x minus the sine of the first angle minus the second angle. And then all we have to do is simplify this. We get 1/2 times the sine of 9x minus the sine of, oh, that was supposed to be a 4x. Gosh darn it. Minus the sine of x. And that's actually it. And we could distribute the half if we really wanted to, but there you go. That's the entire process here for the sum or the product to sum formula. And it's not a very hard one, but it's kind of a handy one every once in a while. Okay, so the last of our problem here, or last of our identities here, is the sum to product. So we went product to sum. Now we can go sum to product. And we're going to use it in this kind of sense here, where we can find the exact value of something. And right now, we could plug this in our calculator and get something really ugly. We can try to do any number of identities here. But what we want to do is we want to use the sum to product. So if you look at your sum to product, we have the cosine of x plus the cosine of y, which gets me an identity of 2 times the cosine of x plus y. So 195 plus 105 all over 2 times the cosine of the difference. So x minus y over 2. 195 minus 105 all over 2. And we're going to do a little bit of simplifying. 195 plus 105 is 300. 195 minus 105 is 90. So we get 2 times the cosine of 150 times the cosine of 45. And those are actually good numbers. And that's the whole point. They're not going to give you ugly numbers here. So the cosine of 150 is negative root 3 over 2. And you can find this on your circle. I know you can. And the cosine of 45 is root 2 over 2. And we simplify this, the 2's cancel, and we get the negative square root of 6 all over 2. Oops, let me erase my page here. All right, so what if I wanted to find the solutions here? Now we haven't had anywhere nothing we can do with this in some of our previous experience yet. So what I want to do is I want to use my sum to product. So it's a sum of two different signs. So this becomes 2 times the sine of 5x plus 3x over 2. So 5x plus 3x over 2 times the cosine of 5x minus 3x over 2 equals 0. And simplify this, we get, okay, 5x plus 3x is 8x, divided by 2 is 4x. And 5x minus 3x is 2x over 2 is x equals 0. And that means if I was to divide both sides by 2, I would say, okay, now we have the sine of 4x equals 0. And we have the cosine of 4x equals 0. Oh, sorry, not 4x. Scratch that. The cosine of x equals to 0. This one's easy. This happens to be 0 at pi halves and 3 pi halves. And then we got to figure out the other ones. And it kind of goes back to what we did in section 7.2. 4x is going to equal 0 plus 2n pi. And 4x is going to equal pi over, no, not pi over, just pi. Pi plus 2n pi. And what we need to do is need to divide both sides by 4. So we get the x equals 0 plus n pi fourths. And we get x equals pi over 4 plus n pi over 4. Man, I'm not paying attention here. N pi over 2, because the cancels. 2 over 4 cancels. So here we get 0 plus n pi halves. That's 0. Okay, so we need to add 0 to our list. Pi halves, and then 3 pi halves, and then 4 pi halves. But 4 pi halves is too big, so we're good with those. Then we need to go down here. N pi over 2 is the same thing as 2n pi over 4. So our first one, when n is 0, we get pi fourths. Then we need to add 2 pi fourths a whole bunch of times. So we get 3 pi fourths, 5 pi fourths, and 7 pi fourths, and another one would go too big. And there we get all 7 of our answers. Oops, I forgot. Forgot one. When we add pi halves here, we get 0 pi halves pi. I knew I should have had 8 answers. All right, so what I'm going to do is I'm going to kind of finish it up right there. Here's your assignment. We're going to we're going to use the rest of the week here to finish this off. Let me go ahead and write this down because I didn't put it on here. Monday is the last day for review. Tuesday, 4, what's that going to be? Oh, it's not even going to be 4 anymore. It's going to be 5-3, I believe. Whatever day Tuesday is going to be. Is our test. So come prepared for that day. You should come prepared every day. But so we're going to use the rest of the week for 7.5 and just kind of any kind of other review you need to do. Monday's going to be the last day review, and Tuesday will be our test. All right, you guys have fun. I will see you guys tomorrow.